here we are at question 23, which I believe is where we left off at the previous video. And so in this reaction, what does the symbol AQ mean after the copper chloride? So AQ stands for aqueous, and something that is aqueous is dissolved in water. Okay, and looking at some of these other answers, and the ionic compound, okay, sure, but you can have ionic compounds that are solid, like this copper carbonate here, for example, is an ionic compound that is not AQ. It is the excess reagent. Well, we don't know that for sure because we don't know how much of the other things there are. It is acquired in the reaction. Well, not exactly. Remember we talked about when we were learning balancing equations that anything on the left is simply referred to as the reactants, anything on the right is the products. So it's not necessarily acquired, we simply start with it. And it must be stirred for the reaction to occur. Well, we don't have any information about that either. So dissolved in water is our answer. Okay, in this reaction, the copper carbonate is the blank. Let's see, the copper carbonate is here, and it's got that S. So the S means that it's solid. And whenever we have something that as a solid in the products, when everything else is aqueous, the solid is the precipitate. Okay, so in the beakers below, show an aqueous, a pair of aqueous solutions with dissolved ions. So if we combine these solutions, what precipitate will form? So we can kind of think about this as some sodium hydroxide, aqueous, plus some iron bromide, aqueous. And we know it's aqueous because we have ions. We have dissolved ions, right? So two aqueous things, if we put them together, we'll get a double displacement. So the sodium is going to go with the bromine, and the iron is going to go with the hydroxide. Okay, so let's take a look at our solubility rules, small as they are, and see if we can figure out what's going on. So our two compounds that we'll have are sodium bromide and iron hydroxide, and it's iron 2. All right, so our halides are down here towards the bottom on the top part of our table. So anything with a bromide will be soluble except with silver, mercury, or lead. And anything with sodium, sodium's right up here, anything with sodium is going to be AQ, soluble. All right, so let's look for hydroxides. Those are on the bottom of the table down here. Those will be insoluble except with an alkali metal or barium, which iron is neither of. So insoluble makes it a solid. So our precipitate will be the iron hydroxide. All right, so which two products will form from this reaction? So again, taking a look at what we have two aqueous ionic compounds, so they'll do a double displacement. So my cobalt will go with the sulfate, and the potassium will go with the chloride. So I know it's cobalt 3 because I have 3 chlorines with it. And then we're going to do sulfate 2 minus. And then our other product will be potassium and chlorine. And I know it's really tempting to try and make things far more complicated than they need to be. You're trying to think of numbers and trying to think, charges and all these things. Just do it as simply as possible. How does a cobalt 3 plus fit with a sulfate ion? And the sulfate is always a 2 minus. How does a potassium ion, which is a 1 plus, go with a chlorine ion, which is a 1 minus? Okay. So with our cobalt and our sulfate, we'll do a double crisscross. So I'll have CO2, SO4, 3, and then our potassium and our chlorine just go together as such. And then our sulfate is going to be a solid, and anything with a potassium is going to be AQ. All right, so cobalt sulfate with the solid and potassium chloride with the aqueous is that one right there. I don't think that's right. Looking at that answer. So let's look at our solubility rules in this slide right here. So there's our sulfate. All right, so sulfates are insoluble unless they're with Dr. Lyon's got to explore here. Let's look at a different table. So sulfates are soluble except with silver, mercury, lead, and okay. So Dr. Lyon was incorrect. So this should actually be AQ. Okay, and now let me come back and explain that a little bit. So with this slightly more complete table. So our sulfates are right down here at the bottom of the top section. So sulfates are usually soluble except with calcium, strontium, barium, silver, mercury, and lead. So cobalt is none of those exceptions. So the sulfate should be soluble. So even Dr. Lyon gets mixed up on the rules sometimes. But rest assured, you will be given that table, so you'll be fine. So aqueous, aqueous. Okay, so our last category are acid-base reactions, okay, and most specifically neutralization reactions. And they're driven by the formation of water. So whenever you have an acid-base neutralization, you always get the same products. You get water and you get a salt. Okay, and to be clear, even though this example is showing what we know of as common table salt, in chemistry, the term salt is any ionic compound. It's a generic term for an ionic compound, okay? So you can always say acid plus base makes water and salt. All right, so let's take a look how that works. So this is how we get the water, because let's take apart the acid-base reaction up here. Okay, so here's the reaction that we showed on the previous slide. Right, so anything that's aqueous can be broken up into its ions. So if I have H plus and Cl minus and Na plus and OH minus, and then over here, liquid things have to stay together. I can't break those up, so that still will be H2O liquid. I won't break that one up. And then the aqueous thing I can break up. Okay, so looking at the chlorine and the sodium, they didn't actually come together with anything at all. They just stayed floating as sodium plus and Cl minus in the water. So if I cancel those out, because they're not actually doing anything, all that I'm left with is the H plus OH minus makes H2O. Okay? This formation of water is a driving force for this reaction to happen. Okay, so a little bit of a challenge here. We're going to stretch your nomenclature brain a little bit. So aqueous hydrobromic acid and aqueous sodium hydroxide react to form water and aqueous sodium bromide. So let's write the molecular equation for this reaction. All right, so aqueous hydrobromic acid. So anything that starts with hydro and is an acid is binary. Right, remember that rule? So a binary hydrobromic acid will just be HBr. Okay, and it says aqueous HBr in the problem. And then aqueous sodium hydroxide. So sodium and hydroxide, NaOH, and it says aqueous. And they react to form water. Right? And mostly I'm just reading the words. I'm not making things up as we go. They react to form water and aqueous sodium bromide. Sodium bromide. All right? And if we look, the reaction is balanced. There are two hydrogens on the left, one here, one here. Two hydrogens on the right. One oxygen on the left, one oxygen on the right. One sodium on the left, one sodium on the right. One bromine, one bromine. So our reaction is balanced. Balancing is usually the last step. All right, let's show the products balancing as necessary. Okay, so think about what we have here. Aqueous, aqueous, which means that it will break up into its ions and we can just swap the ions. So all I'm going to do is take and do a double displacement. Hydrogen goes with the OH, potassium goes with the chlorine. Okay, the other thing to notice is that HCl starts with a hydrogen, that means it's an acid, and compounds that end in OH are usually bases. So acid plus base makes a salt and a water. So I know for sure that one of my products is H2O. And my other product is KCl. And looking, we are already balanced. One potassium, one chlorine, two hydrogens and one oxygen. Don't have to do anything for balancing here. All right, so let's do the next one. So another acid, starting with starting with the H, and a base. So we can know already one of our products is water. All right, so again, two aqueous things, I can do a double displacement. So my H is going to go with the OH, and my barium with the nitrate. And I've already done the H with the OH to make H2O. So my other product is barium nitrate. And that's a barium 2 plus an NO3 minus. So that means that I need two nitrates. So I get barium and two nitrates. And anything with a nitrate is aqueous. Okay, so now I do need to do some balancing real quick. So I have two nitrates on the right and one nitrate on the left. So I'm going to put a 2 in front of the nitric acid. So that gives me 4 hydrogens on the left side of the equation. So I'm going to put a 2 in front of the hydrogen here, in front of the water. So that gives me 4 hydrogens now. And let's see, how many oxygens are there in both sides of the equation? So right now I have 2 times 3, that makes 6 oxygens right here. And then 2 times 1 makes 2 more oxygens, so I've got 8 oxygens on the left. And then I've got 2 times 1. And over here with the nitrate, there's 3 times 2, so there's another 6. So I've got 8 oxygens on both sides. And 1 barium on each side. So there is our balanced equation. All right, let's look at our next one. 2 aqueous things. All right, one starts with a hydrogen, so it's an acid. One ends in OH, so it's a base. And 2 aqueous things mean that I can do a double displacement. So my hydrogen goes with my OH. My cesium goes with my sulfate. So I know that one of my products is water, because acid plus base makes water and a salt. And then my salt, I have cesium plus and SO4 2 minus. So I'm going to need 2 cesiums. And I know that it's aqueous because sulfates are soluble except with a few exceptions, of which cesium is not an exception. All right, so let's take a look at balancing. All right, I can tell right away that I need 2 cesiums on the left because I have 2 on the right. So I'm going to put a 2 here. That gives me a total of 4 hydrogens on the left. So I need a 2 here in front of the water. 1 sulfate, and then let's check the oxygens. There's 4 oxygens in the sulfate on the left, 2 more in the 2 cesium hydroxide, so that gives me a total of 6. And then I look at the right-hand side, there's 2 oxygens in the 2H2O, and 4 in the sulfate, so I am balanced. Okay. So the net ionic equation for any aqueous acid-base neutralization is, and we showed that earlier on with, we can show it again here with this reaction. So aqueous and aqueous. 2 aqueous things, we're going to do a double displacement. Acid plus base makes a salt plus a water, and that's liquid water. So I can break everything up into its ions, everything that's aqueous into its ions. So I can say Na plus Cl minus plus H plus Cl minus. Those are my reactants. And in my products, I get Na plus, Cl minus, and H2O liquid. Okay, I can only break up the things that are aqueous. Okay, incidentally, this is called the complete ionic equation. All right, so what I'm going to do is I'm going to go through and get rid of all the stuff that's the same on both sides of the equation. So Na plus, Cl minus, Cl minus. And looking, I don't have any H plus all by itself on the, oh, I made a mistake there. This should be OH minus. I need an OH minus in there. Sorry, it's not a very good example here, y'all, but it does serve our purpose. Na plus cancels Na plus, Cl minus cancels Cl minus, and what I'm left with, I don't have any H plus on both sides, just on the left. I only have OH minus on the left. I don't have any on the right. And it makes H2O liquid. Okay. Acid-base neutralization reactions always have the same net ionic equation, which is this top one right here. Okay, what is the driving force for an acid-base neutralization reaction? We talked about this as the formation of water. All right, moving quickly through our last few slides here. We're almost to the end. So what type of reaction is this? So looking at what we have two aqueous things. And they do a double displacement, don't they? The potassium goes with the nitrate, the lead goes with the bromine. Okay, so we could just simply say double displacement. All right, but that's not one of our choices. So another thing to notice is the formation of a solid. And when we form a solid, we are making a precipitate. So it's a precipitation reaction. Let's see what we have here. So we could say double displacement again, because if we look, we've got an H going with the OH, and the barium goes with the bromine. So it's a double displacement. But again, that's not one of our choices. So let's see what other options we have. So a compound starting with a hydrogen, that's an acid. And a compound ending in an OH, that's a base. So we've got acid plus base, and it makes a water. So it must be an acid-base neutralization reaction. Okay, and that's going to do it for this chapter's worth of material. You're free to do the speed drill part if you'd like, but you'll be doing that on your own. So have fun with this, and we'll see you on the next video.